Hi, in the exercise of module 7, we will focus on the fault-right through capability of wind turbines. We will start with concepts like saturation, anti-windup, and freeze, and then develop a simple FRT subsystem for the wind turbine model. And finally, we will see the response of the wind turbine in different operating points. In the first part, we are asked to open the model which has saturation, anti-windup, and freeze, and compare the result in the different cases. So here is the model. In this model, there is an error signal which goes to the PI controllers, and the output of the PI controllers are plotted in a scope. Input error signal is generated using repeated sequence interpolated block of the MATLAB Simulink. You can look into the output values and the corresponding time instances. This error signal is sent to the first port of the scope, and also it is sent to the PI controllers and also the freeze. The second signal which goes to scope is freeze signal. By finding the source of this from signal, we can observe that how it is defined. Basically, the error signal goes into a comparison block. Whenever the error is not 0, the output of this signal is 1. Then as soon as it is 1, the freezing is activated, and if it is 0, the freeze signal is 0 also, which means the freeze signal will be deactivated. Then we have the PI controllers. The first PI controller is a simple PI controller without any limits. You can see the gains and the initial value of integrator for this PI. But in the saturation, you can see that there is no saturation or limit. Then the second PI has the limits, which saturates the output of the PI block. We can go into the PI controller and look at the parameters, initialization, and also see that the outputs are limited as we were expecting, but the integrator is not limited. It's only output which is limited. The integrator is limited in the next PI. And finally, we have the saturation on both outputs of the PI and the integrator of the PI. The difference between output and the integrator limit is that the output limit is the limit on the summation of the proportional and integrator part of the PI controller, while the integrator limitation is only on the integrator part of the PI. Then we have the output limitation with anti-windup method. So clamping is used here as a anti-windup method, and also we have the output limitation with anti-windup and saturation on the integrator of the PI. It's good to mention that we haven't considered the anti-windup separately, because when there is no limitation on the PI controller, there is no functionality for the anti-windup part, because anti-windup is activated as soon as the PI is hitting its limits, and it is avoiding the accumulation of the error beyond the limitations. Then in the next part, we have the freezing of the input to the PI. You can see that the PI itself doesn't have any limitation. Here in this exercise, we haven't combined the limitation of PI or anti-windup with the freezing, just to make the understanding of output signals easier, so we know that what we see in the output is because of the freezing of this input signal to 0. I recommend that you change the setting of the PI here also, and see the result when you combine the freezing with the limitations and also the anti-windup. And finally, we have the PI controller, again without any limitation, but in the output there is this freezing block which keeps the pre-freezed value of the output as soon as the freeze is activated. And if the freeze is not activated, the output is the output of the PI. Now let's run the model and contemplate on the result based on the discussion that we had about these different cases. Here we can see the signals. We can hide the freeze signal also because we are not going to discuss about it at this moment. You can interpret this result by looking into the PI controller gains and also the error signal value at each instance. So we can understand that these steps when the error signal is changed are because of the proportional part of the PI controller, while we have this slope which has a slope of 20, and that is a combination of the integrator gain and also the error signal, which is 2. And also we can have a similar discussion when the error signal becomes negative. In the next graph we have the result with output limitations on the PI controller. Here we can see as soon as the output of the PI is going above the limit, the output is saturated, and we don't see any change in the output of the PI as long as the resultant signal without any limitation is above the limit. And we just see the change at the end when the resultant signal is going under the limits. Then we have the result with the limitation on the integrator. In this case, the output hits a value of 2 because we have a limitation of 1 on integrator, but without any limitation on the proportional, and that proportional is adding up 1 more. That is why we see this maximum value of 2. The other point here is that when the error signal becomes negative, we see the change in the output of the PI controller, and that is because when we limit the output of integrator, we are avoiding further accumulation of error. This is very similar to anti-windup that we will discuss further. Then in the next one we have the output and integrator limits together, so you can have a discussion about this graph also. So the important is that now we have the limitation on output, so it is 1, and also during negative error we see the change in the output. It's maybe better if you change the value of the limits here, for example makes it 5, to have a better understanding of these behaviors. I recommend that you do that, and also you can compare the result here with other graphs with another kind of limitations. In the next graph we have the result with output limitation and anti-windup. Anti-windup is avoiding the further accumulation of the error as soon as we hit the predefined limits, and that is why we observe this change in the output signal as soon as the error signal is removed. That is because the accumulation of the error is avoided, so actually our signal is not following the orange one, which is the output of PI without any limitation. It's stop at the saturation limit, and any change which can bring it down will be observed in the output. Then we have the anti-windup with output and also integrator limit. You can discuss about this graph and why it's similar. Finally, we have 2 graphs for the freezing. In the first case, we freeze the input of the PLL to 0 as soon as the error signal becomes non-zero. In this case, the output is always equal to the initial value of the PI controller, because when the error signal becomes non-zero, we freeze the input to the 0, and when it is 0, it means that the error signal is 0, which is similar to the freezing, and that is why we don't see any change in the output of the PI, and it always keeps the initial value. Finally, we have freezing output of the PI to the pre-freezed value. For example, at t equal to 1 second, when the error signal becomes non-zero, we keep the pre-freezed value, which is 0.1, and we don't see any change in the output. But when the error signal is removed, the freezing is deactivated, and the output of the PI without any limitation is connected to the output. That is why we see this jump. Then at t equal to 3 seconds, when the error signal becomes again non-zero, the freezing is activated, and it keeps the pre-freeze value, which in this case is equal to 20. That's why we continue to observing 20 at the output of this block as long as the error signal is non-zero. And finally, when the error signal becomes zero, the freezing is deactivated, and we see in the output of the PI without any limitation. So we discussed different signals here: the error signal, the freezing signal, which is activated when the error signal becomes non-zero. Then we have the output of the PI with limitation and without any limitation, and also the anti-windup with different kind of limitations. And finally, we discussed the result with freezing in the input and output of the PI controller. In the next step, we are asked to open and run the other Simulink model which is provided to make sure that it is running properly. So let's do that. This model consists of a wind turbine which is working in PQ control mode, and it is connected to a grid with a controllable voltage and frequency. You can open this repeating sequence blocks to see the value of the output and the time instances. For example, when grid is simulating a fault, we experience two voltage drops to 0.5 per unit for 200 milliseconds, as you can see in the time values vector. Also, for the power reference, we have a step from 0.2 to 1. So in this way, we are simulating the performance of the wind turbine during fault under different operating points. As always, we can look into the model properties and see that the parameter file is run both from the preload function and the initial function, and which means that the parameter file is already run, so we don't see any warning in the command window, and the parameter values are available in the workspace. After running the model, if we go to the scopes, we can see that the model is working properly. The active power is going from 0.2 per unit to 1 per unit. Also for reactive power, in the reactive power we observe this transient because of the step in the active power, that is the interaction between active and reactive power. Also for the frequency, we see the transient to do the power steps, and similarly in the voltage, measure that the filter bus of the wind turbine. So if you want to know which voltages are plotted, we can follow the signals and see that the first one is the wind turbine and the second one is the voltage of the grid. That is why this voltage is not dependent on the operating points, because it's defined by the grid. In the next part of the exercise, we need to implement an FRT block inside the model to realize the depicted requirement for injection of reactive current during fault. Based on this graph, we can see that for POC voltage under 0.9 per unit, the block needs to be activated and inject a reactive current, and it goes from 20% to 100%, and after that it will be always 100%, which is equivalent to 1 per unit of reactive current. Before implementing the FRT block, let's run the model with voltage drops in the grid voltage to see actually what is the problem or what we need to do. After running, we can see that the voltage of the grid is dropped to 0.5 per unit, as we were expecting. To have an easier understanding of the signals, it's good to add the labels to signals which are not provided even. You can always do that. So let's do it for voltage and run it again. And now we can see that the grid voltage was going to 0.5 per unit, and in the frequency we have some transients due to the fault and also the steps in the voltage. We can observe also the impact of the fault on the active power and the reactive power as well. But to have a better understanding of the situation, we need to look into the current, specifically reactive current, because that is something which we need to follow the grid code requirements. By looking into the reactive current, we can see that it is not following the requirement, because for a voltage drop of 0.5 per unit, we expect that the wind turbine is injecting 1 per unit of reactive current. But here we can see that it is not following the requirement. Also, for the active current, we can observe the signal and see the impact of the fault on the active current. Specifically in the second case, we can see that the active current is saturated, because it means that we need to inject active currents above 1 per unit to be able to achieve 1 per unit of active power. But the active current injection is limited by the limiters in the controller. So that is why it's hitting the limit. While the operating point for active power is 0.2 per unit, we can inject the required active current to achieve this power level. The main thing that we notice by looking into the current waveforms is that the model is not following the grid code requirements for injecting reactive current, or IQ. So that means we need to manipulate the reference of the reactive current during fault. That is why we need to put the FRT block here between the outer and the inner current controller loop. In this way, we will have access to the reference current and we can change them based on the requirements. To save time and make it easier, I have already implemented a simple FRT block based on the requirement. In this block, the ID current is going to the output directly, but the reactive current depends on the control mode. If we are in the normal operation, the reactive current reference coming from outer loop is sent to the inner current controller, while if you are in the FRT mode, the reference for current is defined based on the graph that we have in the exercise document. For detecting the fault mode, we are comparing the measured voltage with a constant value, which is 0.9 per unit, because in the document we see that requirement is defined for voltage levels under 0.9 per unit. And if the voltage is under 0.9 per unit, it means we are during fault, and the FRT signal will be 1, otherwise it will be 0, and the reference current from outer loop is sent to the current controller. But let's take a closer look on this part that we have implemented. For example, if the measured voltage is above 0.9 per unit, the output of this block is not important, because the reference current is taken from the outer controller loops, and the output of this voltage dependent reactive current reference generator is not connected to the output. But for the voltage under that, we can say, for example, for a voltage value of 0.8 per unit, the output is 0.4 per unit, which is consistent with the requirement in the exercise, and also for 0.5 it will be 100%. But for voltages under 0.5, there is a problem. For example, for 0.2 per unit, we will have 1.6 per unit of reactive current in the output, which is not consistent with the requirement, and also it will goes above the limit of the converter. That's why we need to add a saturation at the end of this block to make sure that it never goes above 1 per unit. So we can set the lower limit 0 and upper limit 1, and now it should be fine. Another way to implement this part is actually we can use a summation and add the output of this voltage dependent current generator to the value of IQ, and then freeze the value of IQ, which is coming from the outer loop, to 0 as soon as the fault is detected. So instead of using this multiport switch to switch between the current reference value from outer loop and the one which is defined from grid codes, we can freeze the IQ value, which is coming from the outer loop, to 0 as soon as fault is detected. In that case, we need to also freeze the value of the other one to 0 while we are in the normal operating point. So this is an alternative way to do that. And it's also good to mention that the requirement that we discuss here is just a simple example, and there could be a more complicated grid code requirements either during fault and also post fault. So this is just a simple example to help you understand the grid code requirement for reactive current injection, as well as implementing the FRT block. Now we need to embed the FRT block in the controller. Maybe it's better to separate ID and IQ and define the individual port and define individual input ports for each of them, because the ID and IQ are coming from different control blocks, so it's easier to connect. You can use MUX or DMUX, it doesn't matter, but I personally prefer to define an additional input and output port, so the connection of the blocks looks better. Now we have the FRT block connected. With this block, the ID is sent to the current controller directly, but the value of IQ depends on the operating mode. If it is a normal operation, it will be input IQ to the FRT block, which is sent to the current controller. Otherwise, we have that voltage dependent current reference generator, which defines the value of IQ based on the grid code requirements. After running the model, we can actually see that the block is detecting the fault properly, and the FRT signal becomes 1 when the voltage goes under 0.9 per unit. And also 1 per unit of reactive current is injected to the grid. It's -1, but it is equivalent to 100%. The negative sign is because of the sign convention for reactive power. So it's not a problem. The magnitude here is the important, that we are following the grid code requirements. Also, we can observe the active current. There is a problem here. If we look closer into the D-axis current, we can see that 1 per unit of active current is injected in the second instant of the fault. And we know that according to grid code requirement, we are also injecting 1 per unit of reactive current by the converter to the grid. That leads to around 1.4 per unit. So we need to make sure that this 1.4 per unit is not above the physical limitation of our converter. If it is not above, we don't need to do anything, but let's say that it is above our converter current limitation, and we need to protect the converter as well. So let's see how we can do it. Since it is asked to give the priority to the reactive current injection during fault, we need to limit D-axis current when it is needed. But this limitation depends on the value of IQ. So sometimes we need to limit it, and sometimes we don't need, because IQ is not large. For this purpose, we can use dynamic saturation and define the upper and lower limit at each step separately. For the lower limit, we can set it to 0, but the problem is the upper limit, which needs to be set according to IQ. For this purpose, we need to consider the maximum current of the converter. This maximum current, you can compute it based on the saturations which are defined in the model in the outer loops, and obtain the maximum value. Here in this model, it is 1 for ID and 0.5 for IQ. Actually, the value of the maximum current is not the point here, and it will be known from the converter characteristic. The point here is to help you understand the relation between the maximum current and the ID when we are designing the FRT control block. So we can say the maximum current here is around 1.12, and then we need to subtract the IQ from FRT control block, then use the square of this current. subtract it from the maximum current, the output, then obtain the square root of this value and give it and set it as the upper limit of the d-axis current. Here there is a point which needs to be considered, and that is the deactivating this upper limit for ID when we are not in FRT mode. So I leave it to you to improve this control block such that we don't give the priority to ID during normal operation. Now we can go to ID scope and run the simulation from there to see the change which will happen in the ID. Now we can see that the ID is reduced and it is limited, but the value of ID is now under 0.5 per unit. The value for IQ is right. So to find the problem, probably you have noticed the problem, but to have a better understanding, we can plot the signals IQ from FRT block and also the upper limit for ID which is obtained. We can see that IQ FRT is fine, but the upper limitation is the problem, which is less than 0.4. But we were expecting that it be 0.5 almost based on the maximum current that we are defining. So you see, by plotting the signals, we can always try to understand the problem. Here the problem is that we forgot to put a square in front of the I max. Now by doing so, we can see that the upper limit of the ID is fine, and now the ID is also fine, and it is injecting 0.5 per unit of active current during fault. Another point that I like to mention is this voltage measurement. The measured voltage here is the voltage from a grid if you follow the signals. That is important, especially when we have a large wind farm, because grid code requirements are defined for the point of connection. And here also you can see that the voltage is the voltage at point of connection, actually, not the voltage at the terminal of the wind turbine. And that is important to take into account to use the correct voltage measurement when designing your FRT block. To make it simple, I didn't define new input to the wind turbine model and simply made the go to a global signal and used it inside the wind turbine model. But it's better to define a new input to the wind turbine model and give the amplitude of the measured voltage as an input to the wind turbine model. We can test our implemented FRT block for other voltage levels as well. For example, for a grid voltage of 0.8 per unit, we can run the model and observe the signals. We can see that the voltage drop is correctly detected as a fault mode, and for the reactive current injection, we can see it is injecting 0.4 per unit of reactive current, which is consistent with the requirements for IQ, and the ID is also working properly. Here we don't see any drop in the ID because the injected reactive current is not hitting the limit, so we can inject 1 per unit of active current. Also we can test it for other voltage levels, for example 0.3, and let's make it for different voltages and make the second one 0.1. After running the model, we can observe the currents and see that the FRT block is properly working and injecting 1 per unit of reactive current during fault and taking care of the current limitations if we hit the limit. Now let's bring back the setting of the voltage to the default value and run the model again to make sure that we haven't changed anything for the rest of the exercise. So it looks that the model is working properly, and yes, we see the two faults happening. So we have implemented the FRT control block and gave the priority to the reactive current, and we just need to consider the requirement for post-fault operation of the wind turbine. Here it is asked to simply return to the pre-fault operating point. Sometimes there are specific requirements for the post-fault, but here for simplicity we just say let's return to pre-fault operating points. For that, if we look into the result, we can see that it is going back to the pre-fault operating points, but not instantaneously. We experience some large transient after the fault is cleared. So we need to think of a solution to improve the post-fault response of the wind turbine. For a better understanding of the situation, let's observe the generated references which are coming from outer control loop. By looking into the signals, we can observe that the reference signals which are coming from the outer controllers are not going back immediately after fault, and we see some transients. So that means that we need to do something in the outer loop to remove or at least to reduce this transient response of the controller. We can observe the impact of this transient on the DQ access currents. Considering the first part of the exercise about the different setting of the PI, probably we can improve the situation by changing the setup of the PI. Before that, let's look into the input of the PI controller, which is the error signal. Looking into the input signal, we can see that the transients are present in the input error signal as well. By looking into the PI settings, we can see that it has the saturation and anti-windup properties, while the input signal is experiencing the transient. Based on the first task in this exercise, we can consider using the freezing the input signal to PI using the freeze. In this case, we use the freezing signal to 0 to make sure that the input signal to the PI controller is 0 as soon as the fault is detected. That means that the output of the PI controller will remain the same as the pre-fault operating point. Notice that we consider that before fault the system is in a steady state operation, which means that the input to the PI controller is 0. That is why by setting the input signal to 0, we are not making any change in the output of the PI controller because the input was 0, so the proportional part is also 0, and the integrator will not change when the input signal is 0, and it will keep the pre-fault value. Now, having this freezing in the input of the PI controller for Q axis, we can run the model and see that the post-fault performance of the wind turbine is improved a lot by freezing the input signal to the PI controller of reactive power to 0. But what about the D axis? If we look into the error signal of DC voltage, we can see that here also the error signal is not 0, so probably you might think it's also good to use a freezing for the D axis current as well. So let's freeze the input signal to the PI controller in addition to the saturation and anti-windup which are implemented in the PI controller itself. In this case, if we run the model, we can see that it's actually introducing some transients in the first instant of the fault, which is happening around t equal to 10 seconds. But why does it happen? The important point that we need to consider here is that for Q axis we need to follow the grid code for injecting the reactive current, but for D axis current, which is related to the active power, we don't need to freeze the controller when it is not necessary. Freezing the input signal of the PI here means we are deactivating this controller, which means we are deactivating our active power controller during fault, which is not necessary, especially when the controller is not saturated, so we can inject the required active power without any problem. So why do we need to freeze the input signal and deactivate our active power controller during the time that we actually don't need to deactivate it? And it is an important point to be considered. So we don't freeze the input signal to the PI controller of DC link voltage controller. There are some solutions for improving the performance of DC link voltage controller when it is saturated, and I leave it to you because it's not the focus of this exercise. So we have realized the requirement for injecting reactive current, gave the priority to the reactive current injection, and also improve the controller response to come back to the pre-fault operating point immediately after fault clearance. So we implemented the FRT block and observed the response of this block, but we are also asked to look into the DC link voltage and also observe the chopper switching signal during the different operating points. It's good to mention that the chopper is activated when there is an imbalance in active power of DC link, such that it increases the DC link voltage and hits the limit, so the chopper will be activated to dissipate the surplus power. Here in this case we can see that at the first instant of the fault, the converter is able to inject the pre-fault value of the active power, which means that we will not experience fast increase in the DC link voltage, but during the second instant of the fault, injected active power drops to 0.3 per unit, while the pre-fault value is 1 per unit. We cannot inject 1 per unit of active power during this fault instance because of the drop in the voltage and also the limitation that we have on the D-axis current. So let's look into the current. Here we can see that the FRT is working properly in both cases, as we observed before also, and we are injecting 1 per unit of reactive power, and also for the active current we see that the active current is reduced in the second instance because of the limitations. Now let's look into the voltage. We can observe that the DC link voltage is not experiencing large voltage rise in the first period because the 0.2 per unit of the power which is injected from the generator side of the wind turbine can be transferred to the grid. While in the second instant of the fault, there will be this imbalance in the power flow, and the power that we are injecting from the generator cannot be transferred to the grid fully. So that is why we observe this increase in the voltage during the second instant of the fault. But the voltage is not constantly increasing, and it hits the limit and stops there, and that is because of the chopper. Because in the second instant of the fault, the chopper is activated, and we can see the switching signals for the chopper. You can go into the chopper controller and see that it's like a DC PWM, which is generating the switching signals, and the signal is used to control a switch connected to a resistance. The resistance here is designed such that it is able to dissipate the nominated power during the rated voltage. So we see that the chopper is activated to protect the DC link from constant voltage rise. Also, there is a homework that is asking you to investigate the impact of decoupling and feed-forwards on the performance of the wind turbine's current controller. You can either try to develop the model that we were working on in module 5, or if you are feeling lazy to go back and open that model, you can still use the model in this module and remove the decoupling and feed forwards, and then reconnect them and compare the response of the wind turbine in different scenarios to have a better understanding of this decoupling and feed forwards. And this is the end of exercise for module 7.